as well. You could consider maths as a language. So in a similar fashion, GD&T is a language. And what does it consist? It consists of dimensions, it consists of tolerancing, it consists of symbols that are used in various ways to explain certain things. It has various rules and definitions and guidelines that it needs to follow, right? So why do we need such a language in the first place, and where do we need it? So you might have seen in engineering drawings, everyone here might have gone through the subject called as engineering drawing, right? So in that subject, what is there? We usually draw, have a view of something, side view or top view or front view of some particular component, and we give dimensions. Now, what happens with those kinds of dimensions? Let's say we have a particular phone, right? And we have a drawing of it on the sheet, and we give a particular dimension, let's say 5.5 inches, right? So when I give 5.5 inches, obviously while manufacturing, you won't get the exact 5.5 inches. There will be some kind of variation, right? Because there's no thing such as an ideal dimension. You will get a variation. There's imperfections in the part, surface imperfections that have to go through, more processing and things like that. So things like that are there. Then we also there'll be when creating certain assemblies, like let's imagine this mouse, right? So every part should be made in such a precise way that it fits with each other when we try to assemble it. It should not be like some part, some few millimeters here and there, and then it's not. You might have even seen such parts, where this poor build quality, you see they don't fit together or are loose, right? So this is where GD&T is important, where whatever you're trying to create, you need to get it on a precise scale, right? So that is where GD&T comes in. So obviously GD&T plays a role from the very beginning of product, product life cycle. So right from the designing of the product to actually, manufacturing the product, and after even it's manufactured, when we send the product to, quality inspection. This is where also the GD&T comes into play, where the inspection guy will also know, okay, this is the exactly what the design intent was towards making this part. Why is this part made like this, right? Why is this part of this dimension, and does it pass through the quality tests? So GD&T plays important roles in all of those aspects. Then let's come to the types of tolerancing. Now, how many of these tolerancing types have you learned so far? I think just maybe one, right? If anyone could say, have you ever seen these many types of tolerancing? Anyone? Feel free to guys open your mics and ask doubts and whenever you want. If you raise your hands, I might not be able to see that. So if you have any doubts, just open your mic. Just say, okay, what this page I didn't get this right. So here the question I'm asking is, have you seen any of these tolerancing types before? If you have not seen, that could also be an answer. Okay, no, I've not seen.
Sir, I actually seen that in some cases are in bearing inner diameter is 50 and shaft diameter is 49.90.
Right.
It is different basement tolerance. Yeah.
Right. See, yeah, exactly. That's the point. You can't have the exact dimension or it won't fit. There needs to be some tolerance in some different ways where you give some space depending upon the assembly of the part. So there's total 5 types of tolerancing we have currently, right? So one of them is limit dimension that you can see, where you don't give the dimension separately and the tolerance separately. You give the upper limit that can be made during the manufacturing, and we take the lower limit. Now you can see in this case it's 1.5005. That is the upper limit. That's how thick the rod or shaft can get, or it can get by 1.5, right? So this is a way you can give tolerancing. Now there's also one way unilateral where it's only just a positive tolerancing where only the shaft could get in a bigger, right? So that's the unilateral. So it's one way, just tolerancing. And we have bilateral. So that is both ways. I think you must have seen the bilateral the most, where we give tolerancing, let's say 10 plus minus 1 2 like that, right? So it's both ways. So it could be, if you say 10 plus minus 1 2 it means it could, the part could be 9 or it could be 11 somewhere between that, right? So we have that, space where it's not like if the part is only 10 then only we'll accept it, because that won't be the case. You won't get the exact dimension all the time, right? That doesn't happen when we manufacture the components. There's some imperfections, surface imperfections, shape imperfections. Then we have bilateral unequal, where the lower and the upper tolerance limit are both not equal. In the bilateral one, we have the equal, like upper tolerance and lower tolerance both are equal. They're not equal. Now, geometric tolerance, in which we'll learn today, is something very different, right? You might say this is like looking very different from the other diagrams right here. So this is what we'll try to learn how to read this, the box that you can see right there, right? What is that A and what is that B? Why are there a number in the box and why is the number outside the box, right? So what that all means is how, what we'll learn today, and why has it been such a, why is it done in such a complex way? Why can't we do this? Right? So we'll see about that. Then we come to why GD&T is needed. So what happened was, when our previous normal dimensioning system, the part would get not manufactured correctly, and lots of part would get discarded because they won't fit with the other parts. And I think you've seen in the recently, if you take a case study, lots of Ola scooters were getting, the customers had complaints that the parts were not fitted correctly, the assembly was not right. So this is due to, it's somewhere down the line, the considerations were not correct, that the parts, why are the parts not fitting, right? One aspect could be, the drawings, the GD&T could have been, here and there. Otherwise, some issues in the manufacturing. Manufacturing issues will always be there. That's why you have to control it where you can. That is where the drawing, right? So that is why we moved from normal dimensioning system to the GD&T. So these kinds of mishaps don't happen, because your brand name could get could get bad due to that. People will say, okay, this kind of brand gives cheaply made materials that don't fit and the finishing quality is not good, right? So why GD&T is needed? So first of all is enhanced communication. So in the normal drawings, what engineers first, they had these issues, right, where the parts won't fit with each other. So what they tried to do, they kept the drawing the same, and in the side they used to write a note for everything, like, okay, why is this exactly this size, and why is this tolerance given like this? So we had to write it like an essay. So what used to happen? See, a particular component is worked between a lot of teams. There's the CAD modeler, then there's the designing and testing team, there's the quality control team. So when this drawing passes through all of those guys, there might be some miscommunication that might happen due to language barrier, due to some other kind of, maybe somebody did not take a particular word. So that could also lead to that kind of catastrophic, disaster. So writing, instead of writing that much big paragraph and then you also have to read it, we thought about having language instead, where you could just look at the drawing and understand it. You don't have to go on reading or writing an essay about it. And comes to improvement in reliability and quality. As I told you, the parts that you'll be making will be more, consistency will be there. The same part you can provide lots of times, and there won't be, discarded part. It would be like, the goal usually in the industry is one part out of 10 million should can have certain, issues with it. but that is like one part in 1 or 10 million, right? So that kind of consistency, when you have to maintain, you have to use a very reliable and high quality system. So that is GD&T. Then we have increased flexibility. So that is also a part where GD&T can also help. There's certain, when you go deeper into GD&T, you'll learn how giving certain types of tolerances to a certain component can help you when you're assembling it. Or, sometimes there are variations. Like a single part can attach to this part as well, can attach to some other part as well. So there needs to be that kind of flexibility between the parts, right? So that's also one of the advantages of GD&T. There's lots of more advantages, but these are the very important ones that save company lots of money and time. Then let's come to the standards that are used. So these are, you can say, rule books, right? So I think if anyone is a part of an FSA team, right, you have this rule books, certain 100 pages rule books. So similarly in here also, we have certain rule books and guidelines that people follow when it comes to actually engineering drawing and labeling them and giving them dimensions and like that. So that is a standard followed in every industry. So these are the two most used standards. That is the ASME Y14.5, which we'll be using right now in this session. And there's also ISO 1011. So on the internet, you can find both of these, and you can go through both of these to gain more information. You don't have to really go somewhere else to learn about this. You just need effort and time, and you can learn it by your own as well. So let's come to how you read GD&T. What are the rules? What are the guidelines? So we'll come to this diagram that we have at the end, right? We'll try to read it at the end, but let's see what is the basic thing. So what is a feature and what are the types of the features? Type of features. So feature is something that is a 3D material, right? So you could see on the right, there's a component given, right? So it has certain features, you can say. So it could be a surface, it could be a diameter, or like a hole, pinhole. It could be a slot, it could be an extrusion, right? So all these are representations of a feature. Then the feature is divided into two simple types, internal and external. Now, if you look at it, can someone say which one is internal feature, which one is external feature? It's very simple, any one of you.
Sir, outer diameter is a external feature.
Yeah.
And holes and shaft diameter is internal feature.
Holes and shaft diameter is internal. Okay. So some part you're right.
So
yeah.
The holes are the internal, and the external one is the shaft and the circle.
Right. Yeah, so that is the correct answer. I think the one answer before was also a little bit correct. The shaft is the external feature. It's very simple. Whatever is extruding outwards, or you can see it physically, it's an external feature. Whatever is like a slot or a hole that you have to dent in, that is an internal feature, right? So I think this feature, what is a feature and types of features, is clear. Then we have the feature of size. Now, feature, you understand what is a feature of size. So there's a definition for it, right, that the industry follows. So let's first read the definition and then convert it into simple words. So feature of size is a cylindrical or spherical surface or a set of two opposed elements or opposed parallel surface associated with a size dimension. Now, this is some confusing thing that on first read you might not be able to understand. Lots the whole GDNT is like this. You have to go it through multiple times. It basically means whatever you can measure using a vernier caliper. You have seen vernier calipers, right? Guys? Yeah.
Yes.
So you've seen vernier caliper. So whatever you can, pick up and put a vernier caliper and measure it and say, okay, this dimension, yeah. So that is a feature of size. If you can't do it, it's not a feature of size, right? So then in that also there is two types, that is regular feature of size and irregular feature of size. So both are feature of sizes. Your regular one is you can directly measure it, keep the vernier caliper and measure it. But you can see this hexagon pentagon I've given here, right? So that is a irregular feature of size because you directly won't be able to like measure it. You will be able to only measure like a side, and that will also be not accurate. So what you can do, you can keep a circle like this, and you can measure the radius of the diameter of the circle. So that is an irregular feature of size where directly you won't be able to measure it. Right? Then we have something called as not feature of size. So what is a not feature of size? So on the right one, you can see there are this chamfer and radius. You can see, chamfer and what you can say, uh, the curvature, right? So those features are called as not feature of size because you can't directly measure it. You will have to, have some kind of measuring, some different kind of equipment to measure the kind of radius or the curve that is there, or the slant that is there, the angle, right? So those are called not feature of size. Like similarly, if I tell you to measure the surface of the mouse, you won't be able to measure it directly. You have some kind of probing instrument that will go through the surface, and then you'll be able to measure the whatever the curved surface is there. So those are not features of size. Okay. So this is all the basics that is actually required for building up to what is actually GD&T. Then we come to envelopes. Now, in the previous one, I'm not going in depth about type A and type B because I want to keep this simple for you. You first, learn this, digest this, and then you move forward with GD&T because GD&T can be very confusing in the beginning stages. Then we come to meeting envelope. So I think everyone can understand what an envelope is, right? It's like a shell, like an outer cover, right? So envelope is a similar term that is used here. So let's imagine you have a shaft like the image given here. So what will be an envelope of a shaft? It will be like a pipe, right? A very thin pipe, so which can cover the shaft, right? So that is an envelope. So even in the definition, it's written in a similar fashion. So what is an actual meeting envelope? It is a similar perfect counterpart. So if you have a shaft, what is the counterpart of it? A pipe, like a hole kind of thing, right? So if you put it upon that, you can cover it, right? So in that fashion. So there's a further definition is further explained. Of smallest size that can be contracted to an external feature. It means if it's an external feature like a shaft, it can be contracted to the smallest size. Or if it's an internal feature, it can be expanded to the largest size. So actually, when we are touching the material, so that is the envelope. It should touch the grip the material exactly. So envelope is not a physical thing, first of all. It's a imaginary, you could say. It's just for consideration. Uh, then even in that, we have two types. Everything there's types. There's if you go in depth, there's lots and lots of types. But this is the simplistic one. So there's two types. There is unrelated actual meeting envelope, and there is related actual meeting envelope. So you could see even the diagrams are different, right? So what is unrelated? So you can see the lines are going diagonally. That means they are following the center, the axis of the shaft that is there. So they are going according to the center of the axis of the shaft. And in the related one, they are related to the surface that is given, mentioned. You can see there's a surface called A. It's labeled A there, right? So it's related to that. We are trying to give the envelope to the shaft. So that is the related one where it is perpendicular. We are relating it in some way. We are fixing it in some way. And there is unrelated, which is just hanging through the axis of the shaft. So this is the two variations of the envelope. Now, so all this, whatever we have learned, you will need this when you go further in the GD&T. That's why I wanted to give you an idea about all this. Now coming to material conditions, this is now very important aspect that you need to pay attention. Okay. Now, yeah, I'll just drink some water. So, any doubts till now? Anyone?
तो उस टाइम में नहीं जाते थे तो जॉब को कैसे जाएंगे
Sorry, I couldn't get you.
उस टाइम में नहीं जाते थे तो आप कैसे जाएंगे
Okay, if you could type it in the chat, I'm still not able to get it.
Can you repeat again related envelope?
Related and unrelated. Okay. So, see, the related means it is relating to something. It is not just, see, let's take a bottle, right? Right. So if I want to have an envelope, it would be like a, like a shell for the bottle. Now, if the bottle is just, lying like this and I put a shell, it's an unrelated. If I say that the shell is, or the bottle is perpendicular to something, or it's, sitting here, and then put a shell on it, it's a related mating envelope, right? So lots of parts, what happens? Now, see, when in an assembly, lots of parts are moving parts and lots of parts are stationary parts, right? So in that case, it matters. So there's two different variations of that. Okay. Now there's various more needs that related and unrelated mating envelopes have, but let's not go into it because it will become very confusing. So just have this that features we have to see what is a feature we have to, and we have two types of feature, internal and external. What is a feature of size, and we have two feature of sizes, that is regular and irregular. Now we have envelopes and we have two types of mating envelopes, that is unrelated and related. Okay. Then let's come to material condition.
Is there any particular symbol for envelope? How are
No,
they symbolized?
No. See, they just mentioned it in short form, like AME or UAME. So that is not really required during the drawing. It is something required while you design a part, while you consider, design considerations are there. So that's where it's required. And I'll further tell you where it's required. Okay. Then coming back to our material conditions. So we have three material conditions, that is maximum material condition, minimum or least material condition, and regardless of feature size. So these are the three short forms that you'll usually find it. Nobody will say maximum material condition. They will just write MMC, or they will draw the symbol with a circle and M, and with L circle and L. And if there is RFS, there is no symbol involved. So I'll tell you about it as well. So let's first see MMC. What is MMC? So MMC is basically maximum material condition. So let's take, for example, an external feature, right? If we consider an external feature like a bottle or a shaft, right? What is the maximum material condition? If we say it has a tolerance, or it has a dimension like 10 mm, the shaft diameter dimension is 10 mm, and it has a tolerance of plus minus 1 mm. So it could be 9 mm shaft, it could be 10 mm shaft, it could be 11 mm shaft. So which one of those three shaft is the maximum material, do you think? Where is the maximum material that we get in the shaft? Which size? Anyone?
Can you repeat?
Yeah. So let's let's take an example. yeah, ignore the dimensions given there, right? Let's take a shaft of 10 mm, and I'm saying the tolerance given with it is plus minus 1 mm, right? So the shaft can be manufactured at 9 mm as well, right? Because minus 1 mm is 9, 10 minus 1, 9. It can be of 10 mm, near about 10 mm, or it can be near about 11 mm. So which one of that is the maximum
10.1,
material?
right? 10.1 it is, right? 0.1 plus minus, right?
No, I was just taking example that is given in the diagram. We can take that
Okay.
one also. Okay, I'm taking one because it's a bigger number. We can talk more easily.
Yeah, right.
11 mm, sir.
Right. So if in a shaft, the maximum material condition is 11 mm. So what about a hole? What is the maximum material condition for a hole of the same size?
9.
Right. So you can see in it's just using the same word, but for internal and external feature, it differs a lot. It's exactly opposite, right? So in while manufacturing, the designer always gives this material conditions, right? So I'll talk about how to use this material conditions as well. But for now, just understand, maximum material. If it is for the external feature, it is the largest size, and if it is the for internal feature, it is the smallest size. So if you read these two lines, it makes it very simpler, and you can remember it. Then let's come to least material condition. Now I think you must have got an idea. Least material condition, exact opposite, right? So if you have a shaft, it is the smallest size because that is the least material for the shaft. And if you have a hole, it is largest size. First, that's where the least material is, right? So anyone, any doubts in this LMC, MMC? Didn't understand.
No, sir.
Okay. Then we have regardless of feature size. Now you can also see, yeah. So you can also see there's no M or L mentioned here. That is usually where the M or the L will be mentioned. So if it's not mentioned, it is the regardless of feature size. It means that it doesn't have a material condition, and whatever the tolerance is given, we should go by that itself. Okay. Now, what do you mean? Why would we use this and not
Sir,
other?
excuse me, sir.
Yeah.
Sir, speak loudly, sir. Please, sir.
Okay. Yeah. So why would we use RFS and not MMC or LMC? So basically, wherever we need a very tight tolerance, we don't want the material where we don't want the feature like the hole to not be lot. Don't want the tolerance a lot. We want it to be very exact, where exactly we want it. Like in the terms of jigs and fixtures, we want the precision. There's lots of precision required in gauges also. So this is where we use the regardless of feature size. The MMC we usually use in the automotive industry, and it's not like we don't use other things, but usually in the automotive industry we use MMC, and LMC we usually use in the aeronautics and other industries. Okay. So I'll show you what exactly MMC and LMC how they work. Right. So let's have a whiteboard here. Just a second. Okay, I'll set up a whiteboard for us. Okay. So you're able to see this, right?
Yes.
Yeah. So let's take a shaft, for example, right? Let's say the size is 10 plus minus 1. Okay. Now, if we consider MMC for MMC, right? For MMC, so how actually the table is? So it will be like this: 10 mm, So usually we'll consider like your 11 mm, right? Because we said maximum material condition. So material should be made at maximum 11, right? So if it's 11, the tolerance that whatever we have, so there's also, this is the size tolerance, right? So this is size tolerance. And we also have like a placement tolerance. So let's say this is the axis of the shaft, and where this exactly axis will be placed there, that also we have a small tolerance for that, right? So where exactly it is placed. So in diagrams you also have that. So that could be, let's say, 0.5, a 0.5, that tolerance. And size tolerance we have like this, 10 plus minus 1, and this is positional tolerance, that the shaft can move. It can be a little on the left side or the little on right side, or wherever it moves within this 0.5 m. Now when the shaft is at mmc, we want it to be perfect at 11 mm. So while 11 mm, the whatever this positional tolerance is 0.5. Okay, we take it as 0.5. But when we move away from MMC, so let's imagine it to be 10 mm. Okay, the shaft, we send it to manufacturing and the shaft is 10 mm, comes back 10 mm. Now we need to add 1 mm to this 0.5 of positional tolerance. So it would become 1.5. Got it? If what happens when this is 9 mm? Can anyone answer? What if the part comes back as 9 mm? What will be the positional tolerance? Anyone?
Two.
No?
2.5.
Close? Yes, right. 2.5, right. So you understand, you don't add this again to this. You add whatever the size tolerance was to the positional tolerance, right? So in all cases, you will see the sum will be 11.5. Is that correct?
Yes, sir.
Right. So this is how the
Sir.
tolerance. Yes. Someone has doubts. Guys, just feel free and speak clearly. Okay. So because I think someone in between tried to ask a doubt, right? So if you have doubts, just yes.
Repeat, sir.
You want me to repeat?
Yes, sir.
Not able to understand his doubt. Can anyone tell me what is asking?
All value 11.5, sir.
Yeah, all are 11.5. Any other doubt than that? Want me to repeat anything?
No doubt, sir.
Okay, okay.
Repeat, sir.
Okay, repeat. Okay, yeah. Yeah, just be clear. I'll repeat anything. Okay. So basically, there is the size tolerance. You'll see in the last example that we do. Okay, we'll exactly see how this is, right. So in the diagram, imagine I give dimensions to this, right. I'll give like arrows, and this dimension is mentioned there. So the dimension mentioned in such a way that we have size dimension. Okay, so this is size actual dimension. What is 10? And this is one is the tolerance that the size can have. The part can be manufactured somewhere between 9 and 11 mm. Okay, but since we are considering maximum material condition, we say that the part should be come out at 11 mm. So there's then also the positional tolerance that is involved. So where the exactly the shaft will be placed, that is also having some kind of tolerance, where the shaft doesn't need to be the exact point where you mentioned. It can be little bit flexible here and there. You can put it. So that is also a tolerance that we can have, right? So this is positional. This is size. So if the part is made at maximum material condition, it should have the minimum tolerance that we have given it, right? Which is 0.5. If I if the part is not made at maximum material condition, the amount that we move away from this, so how much we have moved away, 11 minus 10 is 1, right? So we'll add 1 to this positional tolerance, which is 0.5. We'll add 1. What happens? We get positional tolerance of 1.5. So if
But
the,
sir,
yeah.
What is this tolerance? I mean, tolerance to what?
See, which one? You want size or the position?
No, I'm asking you, saying the positional tolerance. So I cannot understand what you mean by that. Positional tolerance. Can you?
Yeah, I'll make you understand. Okay. So when see, this is a very broad example. Usually the numbers are in tiny millimeters and nanometers. There's adjustments here and there. It won't be like, okay, 1 millimeter adjustment. But for example base, so what happens is sometimes if you see, if you have ever seen like a component where there's like a panel, okay, the panel there's a hole cut out for a screw, okay. So the hole cut out for the screw will always be bigger than the screw whatever diameter is there, a little bigger, because there's some additional tolerance they've given. So the screw, if screws sometimes might get manufactured a little big, but still it should be able to fit, right? So in same way, all the parts that you see in lots of components are manufactured in a way, if one component gets a little bit bigger or smaller, it should still be able to fit with each other, right? So that is why size and position tolerances are important. So the manufacturer knows, okay, this much error here and there is okay. The part can get manufactured at 10.5, 11 mm, it's fine. It won't be like, okay, I know I want the part at 10 mm, otherwise I'll throw it in the dustbin. It's not like that. Right? So this is flexibility to the manufacturer. So for size tolerance, we have a size tolerance for the part actually, and positional tolerance is for where the part is getting placed and how much. If you're talking about shaft, the positional tolerance will be counted from the center of the shaft. In a similar way, if you're talking about even a hole, right? So even there, the tolerance, whatever the hole we give, the tolerance will also be from the center of the axis, right? So that's how things are done. Then we come to, you got that for the tolerance thing. Did you understand?
Yes, sir.
Yes.
Yeah. We'll move forward, further ahead, or otherwise we'll get stuck here only because there's lots of things to cover as well.
No, but okay.
Yeah.
Okay.
So,
But I wanted to understand the last one. You said if the shaft will come out as 9 mm, then we will be adding 2.5.
right. Then the position can vary by 2.5. Then it won't be like, okay, no 0.5 only we want to vary. You can vary it a little more if the shaft comes out to be smaller than that. Then it will fit nicely. Right? So there are certain scenarios where MMC is required. There are certain scenarios where LMC is required. Okay. There are scenarios where you don't want to deal with tolerance, you want precision, right? So I've worked in like the manufacturing company. So there we used to deal with microns in microns, right? So like 2 microns here and there, and the part won't fit correctly. So that's how precise the industries have become, right? So that's why you need to be updated in such drawings. So you don't mess up with the drawings, and after the part is created, you give it to manufacturer. A part is created, then the company blames you because you there's lots of money involved also. There's process to all of this. They've made it
Okay.
systematic.
Yes, that's what I'm asking. That if the original size of the shaft is 11 mm and it's coming out to be 2 mm short, so you're saying that we will be adding 2.5.
Yeah, to the position tolerance.
2.5, what will you add? Material or what?
No, not material. That the shaft can 2.5 mm go here and there.
So,
Goes
so
direct.
2.5 is a lot. I mean, that won't be.
Yeah, I know that is just example, right?
Okay.
Yeah, that is just example, so you can understand. If I say okay 10.005, then the example becomes tougher to understand.
Okay. Right.
That's just simplistic, keeping it simple. Yeah, let's come back to the course and come back to the video, the PPT, and let's move further. So there's RFS also. This is where you want lots of precision. You don't want if there's not the part is not made within the certain precision, we reject it. So here also you can see this is the dimension, whatever is given above, right? This is the dimension, right? I was talking about, and this is the positional tolerance that is given in the box. It's 0.2. You can see, and this symbol over here is the diameter symbol. It's a circular feature, right? So that's what. So 0.2 is the positional tolerance of where the center will be of this. So it can vary by 0.2 and the size can vary by 0.21. Right? So it's in such a way that it works. Then let's come to rule 1. Now,
No, what is there no modifier?
Yeah, this is the no modifier, right? Then you have to stick to this. So whatever the tolerance is there, you have to work with this.
And what is A?
Yeah, that is datum. Don't worry, we'll come to that in further slide.
Okay.
Don't worry, we'll learn everything, how to exactly read and what is there. Now, rule 1 is the individual feature of size rule, and how it works, I'll tell you. So this is the exact, definition of it. Now, how it works is we go back to our drawing. Erase this. Okay. Now let's say rule 1 says, the form of a feature. The form, in other words, the shape of a feature can vary according to the size of the feature. Right. So if I say let's take a shaft again. Okay, easy example. If you take a shaft, imagine this is a shaft, right? And we give dimensions, let's say 25. Let's not take 10, let's take 25, right? So the shaft dimension is 25. And if we give, let's say plus minus 1 mm again, okay? So the shaft can be of 26 mm as well as it can be of 27 mm, somewhere between that. So it says that that shaft is still okay if it comes out like this. Now, obviously, you can see this is not what you want in the shaft, but this is how manufacturing works. There's some bends, some issues might there's imperfections, right? So it won't be this big of an imperfection, but you obviously won't get like an absolutely straight shaft, right? There will be some kind of deviation to it. So if the shaft is still, if we take an envelope, right? This is where you want an envelope. So if you take an envelope, and if the envelope size is 26, okay, and the shaft fit, but it's not straight, okay, still the shaft passes the inspection because they've given it like this, 25 polar plus minus 1. So if even if it's 26, we take an envelope of 26, the shaft might be 25 or something. We don't care about that. But if we pass it through an envelope of 26 and if it fits, the part is okay to go. Okay, it's not rejected. So that is what the rule says, that the shape of the component may vary according to the size. So if we keep this size very small, like let's say 0.1, okay.
Sir, it is also dependent on the length of the shaft.
Yes, right. That is also dependent. So if that's what they're saying, no, is size, no? So length also becomes a size factor also, right? So then if we keep this tolerance as 0.1, okay, just give me a second. Yeah. So if we keep this 0.1, so now the shaft can pass? No, it won't pass inspection. It's not correct, right? Because now the envelope should be 25.1 max, right? Otherwise, the shaft is not correct. So, if you want, very precise component, you'll give such kind of, you know, tolerance, right? If you don't want, you feel like, okay, it's fine. We are going to some cheap manufacturer, their precision is not required, right? Because you see, the more precision you require, the more amount of also money you need to spend on that kind of manufacturing and equipment, right? So if you don't want that kind of precision, why would you spend that kind of money? Right? So companies are always thinking about where and how you invest your money. So if a certain part, like I was telling you about certain, screws, they they have, they've given a big hole so it fits easily, and you don't need it to be very precise. Like some instruments like gauges, the pins of those gauges, those need to be very precise because they are, counting minute details. So that's how, according to the application, we decide what kind of dimension and tolerance we give. So that is rule one. Okay. Then we come to rule two. This is the rule of regardless of feature of size that we are talking about. So first they used to give this symbol of S for regardless of feature of size in the ASME by 14.5 in 1982 edition. After in 2009, the thing got revised, the guideline, and now we don't give this symbol. So if it's not there, it means we have to follow regardless of feature size. Okay, that is rule two. Only two rules. Okay, simple. Then let's come to the main, you could say, the masala of this boot camp. That is the geometric symbols. Now there are 14 symbols exactly, right? You can see all of this. They have certain characteristics, certain names, and categories. So form is there, profile is there, orientation is there, location is there, and the runout is there. So they control particular things of a particular component. Now, how they do it, we'll see in the further slides. And there are some extra symbols. So usually you won't be using these many, these all symbols. For starters, you'll be using all these symbols and a few of these like LMC, LMC, and then we have diameter, radius. We will come through all of those. We'll see what are exactly they are. So let's start with form. Okay. So with form, we understand shape, right? We're talking about shape. Or the finish or surface finish. So let's start with the straightness, right? So straightness itself in the name, you understand it's something to do with so I say, see, this is usually where the symbol is, right? This is where you put the symbol that we are currently talking about, this first box. So in the first box, if I place this symbol, straightness, it means the shaft should have a tolerance of straightness, okay, not of position. Since we were talking about, position of the shaft should vary this much. Now we are talking about the shape of the shaft, the flatness time, the straightness of the shaft should only vary by, let's take example of 0.03. So what you will do, so whatever the dimension is, whatever a given dimension is, above that you will have two lines. Okay, in that you will have two lines at the end where the lines would be 0.03 mm apart, and the whatever the part is should lie in between that. So it means it is straight. If it is not, if it going beyond the line, it means it's not passing the test of straightness, whatever you've given it, whatever you want the preciseness of the straightness to be. Because whatever part you design, if you, look at it at a microscopic level, there will be, hills and bumps. It's not, full plane and smooth. different parts need different kind of finish. So not all parts need lots of straightness to them. Some can be either rough. It's okay. So that is to tackle the straightness of a part. Then if we consider straightness for the a shaft, right? Cylindrical straightness. So if we give this symbol, diameter symbol, right? If the diameter symbol is not there, it means surface straightness we're talking about. If the diameter symbol is there, it means we are talking about the axis, okay? The center of the axis of the shaft. So there will also be a straightness. So the axis cannot be deflected more than that tolerance that you have given, right? If you have given a particular tolerance and the axis is little more bent than that, the part is rejected. Then let's come to flatness, similar to straightness, but here we are also going in the two directions, right? Not just one direction. We have two different directions, so it forms a plane. So exactly like a flat thing we want, right? We can give a flatness tolerance. Same, you give a certain number, and then those two planes will be formed. Between them will be the tolerance that you have given. So the flatness of the part should be between those two, tolerance that you have given. Then we come to circular tolerance. Now, also the shaft, if you see now to our naked eye, they the things might seem very flat and smooth or very circular, but in actuality, if you measure it, there are hills and bumps, and it's not uniform shape. So in circularity also, what we do, whatever your tolerance is there, we have an inner circle, we draw an outer circle, and if the if the part lies between those two circles, the outline, it passes. If it doesn't, it fails. Then similar to circularity is cylindricity. Now, cylindricity is a mixture of circularity and flatness, you can say, or straightness. Sorry, circularity and straightness. So you're also looking at a particular cross section as well as you're looking for the straightness of the surface as well. It should be smooth and straight, and it should be circular, both at the same time. So in cylindricity, you draw two cylinders, one within the other, and those two gap between those two cylinders should be whatever tolerance you have given. Now then come to profile of line. Now if it is like a curved surface like this, okay. So what is the tolerance there? There also you give a line above the whatever surface you have, one below, and the gap between those should be whatever tolerance you assign, like 1.03. So the surface of the line should not go above or below that. If it's going elsewhere, like above or below, then it's not passing the test. Then we have a profile of a surface. Now this is a surface, you see, it's a just one 2D line, right? And a profile is like a flatter surface, right? Not flatter surface, but a surface in two directions, not just one plane direction, it's two directions. So similarly, like flatness, profile of line is what straightness is for, flatness is for straightness, for similar in a similar fashion, right? One above, one below, and the surface should be in between those. And let's come to orientation, where we talk about angularity or perpendicularism or parallelism. So here also you see it's very easy, right? So if you're given an angle of 60 degrees, right, and you give a tolerance of 0.03, a line should, whatever the angle line is, should be at 60-degree approx and should lie between these two lines exactly. If it's not, if it's going somewhere like this, like a little bit 60.05 or something like that, and it's going outside this, so it's not right. It's not right if it's going outside this. So in a similar way, let's take perpendicular. Sorry, the names are, I think, are changed here. So yeah, this is actually perpendicularity and this is parallelism. So perpendicularity, you can see this is the surface we want it to be perpendicular to, and it should lie between those two lines or surfaces that we assign. What that is the tolerance. In a similar way, in parallelism, the surfaces should be parallel to whatever surface the other surface we assign. So if we take this bottom surface, should be first of all it should be parallel to that, and there will draw those two lines where it should not go outside those two lines or two surfaces. Okay. Now this is one of the most important geometric symbols, that is the position that we are talking about, right? The positional tolerance, or in some cases people also call it true position. So this is why this is important, because usually whatever features you need, there's usually circular or something like that features which has a center, and having the proper centering of certain parts is what exactly will help them fit with other parts, right? You can have wrong dimensions, that's fine, but if it's not placed in the correct spot where you want it, it will not work. So this is a very important, where in a similar fashion, if we take a position and give a positional tolerance, we can draw like a small circle, and within that only the other center of the circle should be there, right? So so what used to happen, why we started with this circular positioning system, was first we had the tolerance, square tolerance, right? So if we take, for example, like we were taking 10 plus minus 1 without the, see, I will show you on the better. Okay, everyone can see this? Okay. Yeah. So if we take, like 10 plus minus 1, okay, for a center of a hole, right? Okay, like this. And we have, first what used to happen, we used to have square tolerancing system, where if the, tolerance is 0.2, let's take, the hole can be 0.2 direct, 0.2, away from here, little bit here, 0.2 mm here, 0.2 here, okay, 0.2 here, or 0.2, in whatever direction. But what used to happen due to this, it used to form a square zone. So you can have that, but it's better to have a circular zone, because you have more space. Whatever you see, the shaded region is the extra space if you use circular tolerance, right? If you use that plus minus thing in here, so you won't get lots of, what happens when the point is here. So will you reject the part, right? But why will you reject it? Because it's still in the same tolerance zone. So that's why we shifted to circular tolerancing. So you get extra area to place if the part, center of some part comes here. So that's also fine. Okay. Now these are the other symbols. Now what I want you to do is, I think you've understood this. It's very easy. Just I've also given references where you can get this. So just go there and you can find what these exactly mean. So I want you to go out and describe what these four symbols mean. Okay. And we also have the other symbols that we see. So there is diameter, there is radius, right? So R mentioned, it means it's the radius of a circle. If this one is mentioned, it means it is the diameter of the circle. Because in drawing, you might not be able to get which one we are talking about. Now, if what happens when we are taking a spherical like globe, and in the drawing I showed, it will look like a circle, right? So how will the designer or the manufacturer know it's a spherical surface? So, right? So this is where we use S and whatever, like diameter or radius. So the manufacturer or someone else understand that it is a spherical surface. So these are some other symbols that you use often. So there's more, and I want you to go and search what the other symbols means, right? And also go through whatever we have learned through so far, and note down whatever symbols we have learned. Right? Then this is what someone was asking about, right? So this is a datum. So what happens is, let's say we made this mouse, okay? Now we have to send it to quality control while they inspect it. Now, how will I measure this mouse from where? Where is the, where is my center, right? Where will I measure it from? So what we do, first we place a mouse somewhere. So the degrees of freedom of the mouse are restricted. So I place it here on my hand, right? So this is datum A. Okay. So I've placed it here, and now it can't move, right? I can't move it. I can move it like this, right? In this direction. I can move it in this direction. I can rotate it in this direction. I can do three of those, but I can't do like this direction because it's stuck to this now. I can't do this, right? And I can't rotate like this, and I can't rotate like this also. So it's fixed now. So first we set one datum for restricting three degrees of freedom. Then we add another degree of freedom. So now more the mouse is more locked in, and we add a third layer. The mouse is totally locked in, and now you can uh, measure it and whatever process you have to put it through. So you can think of them as anchors that hold the entire part. So let's take an example here. So see, this is like a sharpener, you can see, and let's take this as a blade of the sharpener. You're making the blade, right? So we'll take the blade, and whatever usually the A datum we say, we have three datums. We only need three datums. The A is the primary datum, B is the secondary datum, C is the tertiary datum. So A datum is usually behind the object, right? So if I place the mouse like this is the A1. So this is usually behind the object or under the object. So in our case, this purple wall you can see, this is the A datum behind. So we have placed it like this, and we place it down below, right? You can see here, datum B, right? This surface is datum B. So we place it down here. Now it is locked like this also, and then we place it by this diagonal surface. See, this diagonal surface is labeled as datum C. Now it is completely locked. Now you can exactly see, okay, there is a gap in here, which means something somewhere there was an issue with manufacturing. And if you put it into a part, it will look like this. It won't look, good. In case of sharpener, somewhere some imperfection is okay because it's a sharpener, you won't pay that much attention to it. But let's say it's an important component, a phone or a high voltage device or something like that. So there you need the part to be right. Then this is exactly what a datum looks like. So this is like, let's say we draw an imaginary line to support the part, and the part might have imperfection, surface imperfection, that's fine. So the part gets rested here. So that's like an imaginary surface that we rest the part with. It's just to when you have to check the part if it's correct or not. Okay, then you use the datums. That's where the datums are required. You have to mention them in the drawing. Which surface is which datum. Then this is datum targets. This is a little complex thing. But what happens if this, let's say this surface is not there, this surface is also curved, right? Lots of things won't have a flat surface, right? So if we have surface like this, how will I, get it supported by a plane? You can't do it, right? So in the such example, we use datum targets, which are like, let's say, if we can't have a surface like this, we'll just use like a point, like a stabilizing thing, and we'll stabilize it here. We'll put one more here, and then it will be stable and it won't move a lot, right? So like this. So you can see there are three types of datum targets. So one is this, the point target, where you just have a singular point and you have to mention it in the drawing by a symbol like this. So you will draw a symbol like this and you will just mention like point it towards where exactly the point is, and you'll mention this. So A1 means datum point 1. Okay. You can similarly name other things as well. Then we have circular target area like this. So if you want a flat area, you don't want a point, you want it to be rested on a flat area, right? Then you have circular area. So then you'll give the radius or diameter of the circle as well. If you have a square area, instead of circular, you can have square area as well. And you can have rectangle one as well. So rectangle, you note it like this. Square, you see it like this first. All sides of square are equal. So you just mention one dimension. Right? And then you also have target lines that can be able to see whatever these three lines are. These 1, 2, and 3 are to able to hold the part in the particular position. It won't allow the part to go elsewhere. So the part is rested down, and it's also rested here and here, like back also. So then you can start and figure out where the part is. Then you can start and measure if it's correct or not, if the angles and the curves and everything is right or not. Okay. So this is how it's changed. Now let's come to the finale of this this session. It's been a long session. Might have been very confusing, and it's okay if it's confusing. You might have doubts, but the important thing is after this, you go through. I've given references below. You go through those references, and once you go like 2 or 3 times, that's when you start to understand certain things. It's like certain concepts of maths. So now let's see if I can read it or not. So there's this leader arrow. Okay. Then we have the geometric symbol that we learned, right? 14 symbols are there. One symbol you can put. Or if you don't want, it's not necessary for every, control frame. Each control frame, you must have a symbol, right? So this is in the first box, you put in the symbol. In the second one, you put in the, if it is a circle, so you need to put a diameter or a radius or something else, right? If it's square, you put a square, right? So like this, there are various symbols that you can put in. Otherwise, if it's a normal dimension, you don't put anything. Right? So this is basically the tolerance zone that you have created. Dimension is something else. So dimension is basically you've given 10 plus minus 1, and this is the positional tolerance of that part. Then this is the material modifier. We've also learned about those. So here we've given maximum material condition. Then we have the three datums that are required to hold the part in place. Okay. Now let's try to read this. Okay. Now there's this symbol and this one. Okay, yeah, this one we can read. So this one we won't be able to read because you've not learned about circular runoff. And I want you to go by yourself and figure out this one. Okay? But other ones I will talk about them. So here you can see, let's talk about datums first. A is given here. That means this whole surface that you're looking at is datum A. So the part will be rested like this. Now you know how the part will be rested, right? First you won't be able to know otherwise, right? The designer would have to tell you, okay, put the part like this. It's supposed to be placed like this. Now you know that the part has to be placed with respect to this surface like this. Okay. Then what the consideration is there that this part is 10 mm and it can be plus minus 0.5 mm, okay, thick. So it could be 10.5 or 9.5 mm thick, right, between those two values. And the straightness should be between 0.05. So if we place two lines, right, if we place two lines on the surface, it should be between those lines. It shouldn't go, elsewhere, right? So that is one thing now we've learned how to, see. Now let's come to our second datum, right? So this datum is P. So somehow we'll also, support this part, and that's how the datum is also supported. Now more degrees of freedom are arrested. Now this part, as you can see, is the shaft and has the perpendicularity symbol. That means it should have a perpendicularity. That means two perpendicular lines should be placed with a distance of 0.1 mm. Then maximum condition, material condition is applied. If it is not applied, whatever we have the size dimension, it will start varying. As I told you, right? We'll start adding. So let's say 25 plus minus 0.25. So upper limit is 25.25 and lower limit is 24.75. Now, if the part is at 25.25, okay, what is the if the part is at 25.25, what is the tolerance? Anyone can answer? Okay, maybe you guys. Yes, right, correct. So if for maximum material condition, I told you, if the maximum material condition is achieved, which is for a outer external part, 0.1, so 0.1 will be maintained. If it starts going away from that, right? So if let's say if it is at exactly 25, right? It's not at 25.25. So 0.25, it is away from that maximum material condition. So that 0.25 you add with 0.1, so it becomes 0.35, correct? So that's how you, yeah. So that's how you design. Now, in a similar way, let's come to now this datum C. So this underneath this whatever surface is there is the datum C. Okay. So here also we can see the dimensions are already given, and we need the profile of the surface. So as I told you, if it's like a curved surface or some bends are there, the surface we also again put two lines between that surface, and it should land between there. If it's not going up, if it's going above or below that two lines that we have placed, this imaginary line, it's not right. Then coming to the last one, right? This one, let's leave this one for you guys so you can figure it out what's written out. It's usually for a curved surface as well. Okay. Then let's see this. So these holes are given below. So it's written 3x because 3 holes are there. And we have the diameter because it's a diameter, right? Diameter 9 plus minus 0.25. Okay. So it means it can be big or small. Then we have the positional tolerance. This is also a diameter because it's a circle. So positional tolerance will also be always circular. And we have 0.5 for maximum material condition. Now here also you see the B and the M, but that is something when you step into very complex GD&T, there's where you use it. I won't be teaching it in this session. If you have any feedback, if you want to learn more about this, I think you've gotten a form and you can write in that, right? So in that way, you might be able to cover this. So currently, you won't be able to cover this. You can do it on your own as well. So I think you must have got an idea how even everything, at least you know how to read it, right? Now it's up to you to put in efforts and see what is used where and how the design process is used. But the most important part where it takes effort is learning the language. So this is also a language also. English you didn't learn in one day, right? So this is also something that you have to revise it a lot. You go through the rules again and again. What are the symbols? What do they exactly mean? And I'll let you know that this might be discouraging, but this language is always evolving. It's not like okay, this is fixed. Right? In few years, we might get a revision of this. Right? So there's also always evolving languages. So,
Sure.
yeah.
Sir, any thermal expansion is directly affected on tolerance?
No. You don't consider that in drawing. You consider it while designing the material. When you're actually, selecting the material. So that is in the design phase. This is where, you're conceptually drawing things. And it's better if you do, if it's something, if you have the knowledge of, thermal analysis and everything related to thermal and expansion, it will make you a better engineer because you'll design it according to that. So if a part has lots of thermal expansion during summers, so you say, okay, I need to, keep the size small or something like that. You think.
Sir, but in case of my shaft is steel and my casting component is wrought cast iron, so it is affected?
Yes, so it will be affected, and see, this is why in companies, if you go, it's very amazing to work with all those engineers because you won't be doing everything by your own. There will be someone else will be in charge of those materials, and you'll have to discuss with him. Okay, can we use this? I'm setting this dimension to this. So he'll say, okay, but if you go back and forth, so this is how the process in the engineering side. So I don't know exactly what will happen when you take these two materials, but yes, the industries do consider this. This is how the design process goes and goes back and forth a lot, and this is how finally we get a component. So it's good that you're thinking in such a way, where the component will be, what kind of treatment or heat is applied to it in the environment.
Yes, sir. But sometimes seasonal effect is affected.
Right. Yes, that's
So that's why I asking you the thermal.
Yes, it's good to consider that. Yeah. Anyone else? Any doubts? You can.
So from where can we study more about this?
Yeah. I'll show you the references. Okay. So this is the 3 references I've used. Okay. So I've mentioned YouTube. So there's some channels. If you just type in, GDNT basics, there's some 3-4 channels that will appear, and they have playlists. To go through this playlist, I'll put videos, and you can even come to us. We teach you that we have in a certain course. And there's this one site called GDNT and Basics. You can go there also to learn about symbols. And other than that, you can take the whole rule book and you can read it. It's available online for free. Okay. So the rule book is the best way to read it, but you might get confused because it's written in a very scientific language. But do try to go through these.
So the first one is the rule book, right?
Yeah, ASME 14 Y 14.5 2009 edition. You can write it down. So what we did today was just like scratching the surface of GDNT. That's lots more to learn. And even I tried to compress it into something small. You might have doubts, and it's something that only will be solved when you further try to learn more and more about GDNT. That's where you will be able to solve it. And I think in GDNT Basics, this website, they also have a forum where you can post your doubts. If anytime you have doubts regarding GDNT, you can post it, and there's a group of engineers, and maybe they can help you. You can have discussions. Why is this rule this way? What does this exactly mean? If you get stuck in any rule within the rule book, there are forums where you can discuss about this. So maybe what you guys can do, the next component or the drawing of the component that you try to make it in with GDNT knowledge, and you can also mention it in your resume when you're building it. That once you get all the knowledge of GDNT, you can mention it in your resume that you have GDNT knowledge, because that is what exactly the industry looks when they're looking for a CAD engineer or a design engineer. They must have GDNT. So whichever book used, it's okay. Anyone else? Otherwise, we'll close this session. Okay. So I hope you guys learned at least little bit, or at least got the seriousness that is there in this subject. It's very important to learn if you're trying to become a design engineer. And even I'm learning it myself, and I've not learned it completely because it's slow. It's a vast subject, but do try to learn. Right? Okay. Then I think we'll end it.
So, audio, turn on your audio.
Okay, my bad. Yeah. So if you have any other doubts, you can directly ask me. Otherwise, we'll close this session. Please do try to go through this. Yeah. Yes, sir.
I'm asking, I was just asking that do you have the references?
I'm not able to hear. There's lots of mic disturbance. Can you type it in chat?
I'm asking, do you have any other website or anything like that from where?
See, I don't have anything else. I just refer to these three.
Where are you looking for? I mean, are you taking help of any specific book or anything?
No, these will be enough for you. YouTube is a vast library. You find a lot there. And other than that, I have some seniors I can ask my doubts to. Otherwise, in a similar way, yeah. Yes, Vinay?
Sir, link of feedback form.
Okay, I think it's in the chat, right? Okay, we don't have a feedback form, I think. Okay. Acha, do one thing, otherwise, I'll give you my mail. Okay. If you have any further doubts, just mail me. Okay? Yeah, there's this feedback form. It's in your chat.
What about the mail?
Yes, Arjun?
The mail you're saying that you
Yeah, okay, I'll let you the mail as well. You can mail me. I've mentioned my mail, you can mail me. Okay, I think Avinash is asking about as a design engineer, which thing knowledge of course is needed for a good design engineer. See, having your basics cleared and having worked on lots of design projects, make a lots of components, projects and reports on that, and have a portfolio, I'd say. So you can search on YouTube what kind of portfolio does a design engineer have and try to create that. And whenever you go for an interview or whenever you send someone your resume, try to send a PDF of that portfolio as well. Okay. I'll end it here, guys. Thanks for coming, and I hope you've learned something, and hope you'll continue to learn and grow. Yeah, so that's it from me. Bye. Bye, Avinash.
Thank you.